Hello, everyone. Good evening, and welcome to the third lecture in our 2022 lecture series here at the Huntington. I'm Dr. Jeff Rich. I'm an astronomer and the outreach coordinator at the Carnegie Observatories. Before we get started, I'd like to thank the Norris Foundation for making the series possible and the Huntington for hosting us for the 20th anniversary of our lecture series. Dr. Mulcahy couldn't be here tonight, so I've been asked to introduce tonight's speaker, Dr. Paul Butler. Dr. Butler has bachelor's degrees in chemistry and physics, as well as a master's degree in physics from San Francisco State University, and a PhD in astronomy from the University of Maryland. He and Dr. Mulcahy actually went to grad school together, so if you have any questions. Over 25 years ago, Dr. Butler pioneered one of the first observational techniques for detecting planets around distant stars, detecting the tiny wobble caused by a planet orbiting its host star. He designed and built the iodine absorption cell system at Lick Observatory used to make these measurements, resulting in the discovery of the first 5 of the first 6 extrasolar planets ever discovered. This instrument has become the standard for precision Doppler studies, and he's designed and built instruments used at professional observatories all over the world, including our own Las Campanas Observatory. Dr. Butler continues to improve upon measurements of stellar Doppler shifts with the ultimate goal of finding planets that resemble Earth. He's here tonight to tell us about the history of our understanding of Earth's place in the cosmos, how our discovery and the hunt for extrasolar planets helps us understand that place, and future prospects of directly observing an Earth-like planet around a nearby star in the future. So, without further ado,
standing in the wings over here, I could only see those 3 empty chairs in the corner. I thought, oh my goodness, nobody's here. So I'd like to thank you all for coming out tonight. For many of you, this might be your first outing in quite a while. This is my first public outing in more than 2 years. So a lot has changed. And I feel as though I've changed too, and it's not just because I've passed on from the carefree youth of my 50s into the decrepitude of my 60s. So it just seems like too much to take in, too much to comprehend. So let's start again. The field of exoplanets is one of the newest forms of astrophysics, and yet exoplanets stretch back literally to the very beginning of science. In the year 2000, the National Academy of Sciences in the Decadal Survey of Astrophysics wrote, "The discovery of extrasolar planets in the past decade was one of the most remarkable, I've taken my glasses to read, most remarkable achievements of the century and the culmination of centuries of speculation." Then 10 years later, in the 2010 Decadal Survey, they wrote, "Extrasolar planets are one of the 3 pillars of modern astrophysics. The foremost goal of extrasolar planet research for the next decade is the discovery of nearby habitable planets." So this is pretty good for a field that's only existed for 25 years. When I began working in this nascent field 35 years ago, you could have held an extrasolar planets meeting in a TARDIS, I mean a phone booth. Back in those days when I was asked by other astrophysicists what I was working on, I would hem and haw and I would say, I'm working to improve precision velocity measurement. Because if you told people that you were looking for extrasolar planets, you might as well tell them you're looking for little green men or for unicorns. And the most likely reaction would be that they would either laugh in your face or they would slowly back away, like you smelled bad, or like you were trying to peddle some new age religion. So at the time, extrasolar planets were a lot like SETI. there was an entirely theoretical field, a field for which there was literally no objects to study. Being a theoretical field, theorists rushed in to fill the void. They concluded that all planetary systems will resemble the solar system. They'll have small rocky planets orbiting close to the host star, gas giant planets orbiting further out, and all of the planets will be orbiting in nested concentric circles. This belief was widely held by everyone, from the most famous astrophysicist to popular culture, Star Trek, Star Wars. With small variations, everything will look more or less exactly like us. The only question was, what fraction of stars had planets? Estimates ranged from nearly 0, but at least 1, to nearly every star. And so while the field of exoplanets spans the last 25 years, science itself is only 400 years old, the span of 4 long human lifetimes. Planets were the central motivation in the development of science. Prior to science, life was miserable, brutal, and short. Until the past century, life expectancy was 35 years or less. The vast majority of people were illiterate. Lightning, earthquakes, disease, childbirth, droughts, floods, these were the norm, forces beyond comprehension, controlled by higher powers. One of the few constants, though, was the sky. Though the stars were unknowable, the patterns they formed were fixed, unchanging, and slowly drifting from night to night, repeating every year. The sky was eternal, and almost everything else was chaos, hunger, and death. Early religions were perhaps the first attempt to organize and understand what was going on. The sky was central to these efforts. The sky was the home and the playground of the gods. The sky was the place of perfection, of heaven. There was one problem, though. The planets, they move. That the planets move in and of itself is not such a problem as long as they move predictably, and to first order they do. The problem is that sometimes the planets reverse their course. So here is, I wonder if this thing has a laser. Hey, awesome. Things don't usually go right for me, so I'm going to take this. So this is Mars in 2003 over a course of a couple of months. And so you can see it starts off moving nice and reasonably, and then suddenly it reverses its path and goes backwards, and then reverses back and goes on forward. This is called retrograde motion. So the issue is, since the heavens are the place of perfection, and the only perfect shape is a circle, this is an affront to all that is holy and decent. So 2,000 years ago, Ptolemy suggested a solution that maintains the circular perfection of the heavens. In the Ptolemaic system, the Earth, of course, is the center of the universe, and you would like to have your planet simply move in a perfect circle around the Earth, but that doesn't work. We just saw the damn thing reverse. So what Ptolemy did was he has a second circle that circles the first circle, and he puts the planet on that. So it's circles within circles. So this is called an epicycle. And it does a nice job of giving you a way to have this pattern of the planet reverse against the background stars. The problem is that as you continue to take more and better measurements, this thing, the predictions simply don't follow what you observe. What they introduced was, it's like the old comic line, more cowbells. In this case, it's more epicycles. So, okay, one epicycle doesn't do it, so you add a second epicycle. You've got the Mars on a circle that's on a circle that's on a circle. And that, in fact, everybody in science and engineering knows that if you simply keep adding more free parameters, you can fit anything. And this did a better job than one epicycle, but again, as you've made more and more better measurements, this thing still fell off of the predictions. So for about 1,500 years, they kept adding epicycles. And by the time this whole thing collapsed in the 1500s, Mars was sitting on top of more than 50 epicycles. So the poor person that had to calculate the model had to work through, and this is with paper and pencil, no computers, no slide rules, no nothing. Paper and pencil had to work through 50 of these circles, and then you still ended up with a really crappy prediction. So of course, Copernicus was one of the first people to suggest a way out of this. His idea was, okay, let's just get rid of the Earth being the center. We'll put the sun at the center. We'll demote the Earth to being a planet. We will keep the perfection of circles, though, because it's all heavenly, it's all perfect. So in this model, the sun is the center, and the Earth and Mars are both simply in circular orbits going around. And the nice thing with this model is you get this nice natural explanation for as the Earth catches up to Mars, Mars appears to go backwards, and then later on, the line of sight goes in the same direction. So you get this nice retrograde, and it pops right out, and it's much easier to calculate. The problem is, it wasn't a whole lot more accurate than the epicycles. It still didn't match the models. So one of the major problems with inventing a new way to organize and understand what's going on is that you face opposition from the groups that are already invested in the business. Similar to the opposition that the solar and wind power have by the legacy oil, gas, and coal companies today. So Copernicus was well aware of the problems he might face from the church, so he cleverly waited to publish until he was on his deathbed. So it was up to the next generation to take these issues head on. So for the folks in the next generation, Giordano Bruno was easily the most fiery. And in 1584, he writes, "There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. The countless worlds in the universe are no worse and no less inhabited than Earth." So basically, over a generation, Copernicus's idea, at least for we're talking the fraction of people who were literate, who could read this stuff, it wasn't even 1%. But for the few people who could and who were farsighted enough to figure it out, not only have they now jumped to the Earth as a planet, but they've jumped to the sun as a star, and that other stars probably have planets. Exoplanets literally predate science. They're in the early lead up to the invention of science. So Bruno was not as farsighted maybe as Copernicus. Copernicus realized he could get in big trouble. Bruno just ran straight into the trouble, and things did not turn out well for him. So the process that led to the invention of science produced the first planet ever discovered in history, the Earth. All the other planets at that time had been known to antiquity. They'd been known to cavemen, right? So the Earth was the very first planet that was ever discovered. Immediately people wanted to know about extrasolar planets. But finding planets around other stars is hard. The stars are a long way away. The planets are very small and faint. It took the better part of 4 centuries of development before the first exoplanets were found. So how are planets found? There are currently 2 primary methods. The first method is the radial velocity. I'm showing it first because this produced the first batch of planets. And in the radial velocity technique, you never directly see the teeny little planet. All you ever see is the star. This is actually common for most of the techniques that are out today. So as the planet orbits the star, it kicks the star into a small counter orbit, so that for half of the orbit, the star is approaching the observer on Earth, and the light gets shifted to shorter wavelengths, bluer. And for the other half of the orbit, the star is moving away from the observer on Earth, and the light gets stretched into longer wavelengths, redder. This is identical to this is the Doppler effect. And you get Doppler effects with anything that has wave motion. So light is wave motion, sound is wave motion. And everybody's familiar of the train whistle coming towards you being shifted to higher pitch, and then moving away from you, it's shifted to a lower pitch. This is the exact same process. So if you can measure Doppler velocities well enough, you can find planets. People have known this for 100 years. The problem was that measurement error until just recently was about 300 meters a second. So here's what our own solar system would look like. Imagine we're aliens, we're orbiting some other star, and we have this Doppler velocity technique. And we look back at the solar system, at the sun. This is what we'd see. The reason I like this diagram, first of all, it's very old, so I don't have to build it again. But secondly, it starts in the year of my birth, and it basically goes to the current day. And if you could measure the Doppler shift of the sun very accurately, you'd see that it goes up and down by roughly plus or minus 10 meters a second, and that it's got this repeating pattern every 12 years, peak, 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 peak. That's Jupiter. What we're literally seeing is the reflex motion of the sun because Jupiter is tugging on it as it orbits, and you immediately can read off of this graph the orbital period of Jupiter. The second thing you get is the amplitude. This thing is going up and down by roughly plus or minus 10 meters a second. You put these two things together, and you can actually work out the mass of Jupiter. It turns out with Doppler velocities, you also get almost all the other orbital elements. In particular, you get the shape of the orbit, how circular or how eccentric it is. The other thing you'll notice is the peak rises, then it falls, then it rises, then it falls. That's a little bit odd. That's Saturn. Saturn has an orbital period of 29 years, and it causes the sun, it tugs on the sun by about plus or minus 3 meters a second. So basically, with the sort of state-of-the-art precision we have today, if we were alien astronomers, the two planets that we could detect in the solar system would be Jupiter and Mars. So the very first planet was only found in 1995. And this is the famous 51 Peg. This was initially found by the Swiss group, Michel Mayor and Didier Queloz. And this is shocking. This is days. This is time in days, and this is the velocity of the star. And you'll see the peak repeats every 4 days. So when this came out, this was stunning. Nobody had ever guessed that there could be a planet in a 4-day orbit. I mean, many people discounted it just because this was so stunningly nutty. This was announced in October of '95, and we had 4 nights on the Lick Observatory telescope up near San Jose a week after it was announced. So we threw all of our resources at this, and these are observations from the first night we had, and then the second night, the third night, and the fourth night. And one of the problems we had was computers were so slow then, it would take us about 6 computer hours to reduce an individual velocity that was taking 5 minutes at the telescope. So we threw all of our computer power at this, and about midnight the day following the final night of the run, and when we saw this, we were stunned. Mayor and Queloz were right. So we continued following this heavily, and this is our first month of data. And you can see this thing just goes up and down like a metronome. And in particular, this type of curve is called a sine wave. Very smooth, almost like an S. And that tells you the shape of the orbit. This thing is almost perfectly circular. If the eccentricity is equal to 0.0, it's perfectly circular. And this is like basically within measurement error, perfectly circular. And with the amplitude being plus or minus 56 meters a second, this thing is in the ballpark of a half a Jupiter mass. So this is a giant planet. Jupiter's 300 Earth masses. This thing's like of order 150 Earth masses in a 4-day orbit. Absolutely stunning. One of the cool things about, so these things are now dirt common, right? I mean, hundreds, thousands of these things are now known. But one of the very cool things about it is that you can put an entire diagram of the system on a piece of paper to perfect scale. It's a Jupiter-like planet, so it's about 1/10 the radius of the host star. In this case, the orbital radius is about 11 times the radius of the star. whole thing, that's actually to scale. And being in a 4-day orbit, it's really hot. It's 1,300 degrees Kelvin, something in excess of 2,000 degrees Fahrenheit. So it's roasting hot. And that's how these things got the name hot Jupiters. So one of the other really early planets that came out of all of this work is 16 Cygni b. This star is kind of fun. There's about 9,000 stars in the Bright Star catalog. This star is the closest solar analog in the entire catalog. If you put the spectrum of this star on top of the spectrum of the sun, you cannot distinguish them. And like the sun, it has a planet. In this case, you can see this repeating period, about every 800 years, a little bit more than, or every 800 days, a little bit more than 2 years. And the amplitude's about plus or minus 50 meters a second. But the thing that immediately stands out is the shape. This is not sinusoidal. This looks like a sawtooth. So, like I say, from Doppler velocities, you get the shape of the orbit. And in this case, the shape is extraordinarily eccentric. If you overlay it on the solar system, you see at its innermost point, it would go inside the orbit of Venus, and at its outermost point, it would be like halfway between Mars and Jupiter. So this is a roughly 2 Jupiter mass thing. If you put it in our solar system, we wouldn't be here. This would be a giant gravitational bowling ball, and it would simply wipe out the entire inner solar system, gravitationally slinging everything out. So the first batch of exoplanets defied all the theory of the first 400 years of science. And in fact, we now know today that most planetary systems look nothing like our own solar system. Entire classes of planets, hot Jupiters, eccentric planets, and another one I'm about to talk about next, were entirely unpredicted. So even the smartest theorists and science fiction writers are not all that bright or imaginative. Theory and dogma are no match for observation and experimentation. Still, the early days of exoplanets were great for media coverage. You could find just a couple of massive planets and make the cover of Time magazine. So another one of these really odd planets that emerged, this is from our Anglo-Australian Planet Survey, sometime around 2007, is this set of Doppler velocities, velocity versus time, again in days. And you notice each one of these ticks is a day. So this is about a month and a half. After much cajoling and screaming and crying, we managed to convince the Time Allocation Committee to give us a month and a half straight. This has never happened before. And this is one of the things that almost immediately popped out. We had a handful of observations. Typically, we get maybe 3 or 4 observations of a star a year. And so we had like an observation here, and then an observation there, an observation there. Couldn't put it together. When we had this thing every single night, this immediately popped out. Of course, this is also because measurement precision was getting better. But you can see there's this repeating 4-day period in which the amplitude is about plus or minus 2 or 3 meters a second. And then there's this longer period, about a month. So again, this is a nearby sun-like star. Another one of these stars is very similar to the sun. And this 4-day planet is about 5 Earth masses. So this was freaky at the time. We now know these things are more than dirt common. Something like 30% of all stars have these kind of planets. They're called super-Earths, things that are between an Earth mass and a Neptune mass. And then here's that second planet we saw, the 1-month period. It's about a Neptune mass. And then if you have a longer data string, you can find a third planet that's about 2 Neptune masses in about a 90-day orbit. So these things just kept getting weirder and weirder and weirder as time went on. So the second technique that is very commonly used for finding planets, and in terms of total number of planets found has overtaken Doppler velocities, is the transit technique. So in the transit technique, you have to be a little bit lucky. The orbit of the planet has to be perfectly aligned with the observer on Earth so that the planet crosses the face of the star. But as it crosses the face of the star, to first order, it's simply a black dot. So if you're measuring the brightness of the star, it will suddenly dip as the planet crosses the face of the star. And if you observe, say, 2 of these in a row, The time difference from one dip to the next will tell you the orbital period. So that's really cool. So how do radial velocity and transit detections differ? For radial velocity, we are it's ground-based, old-fashioned telescopes stuck on top of mountaintops, and we're primarily observing the nearest stars out to about 150 light years. There's about 4,000 total stars that are really good targets for this, out to 150 light years. The radial velocity information gives you the planet mass, the planet orbital period, the orbital shape, and you typically need to observe one or more orbits. Obviously, the more orbits you observe, the better, but once you're at one orbit, you've got a pretty good idea that you've made a detection. So the transits, the planets have to be in orbits that are nearly perfectly aligned with the observer on Earth, right? As long as the orbit's like this and it crosses the face of the star, you're good. But if the orbit's like this, you never find anything. It doesn't cross the face of the star and there's no detection. The transit information gives you the planet radius. Doppler velocities give you the planet mass. This is actually really important. They provide complementary pieces of information. And they also provide the orbital period. They do not provide the orbital shape. And if your only detection is by transits, you typically need 3 orbits to be observed. The requirement of near-perfect orbital alignment for transit detections, such that the planet crosses the face of the star, severely limits the fraction of planetary systems that can be found with the transit technique. Again, the alignment has to be just about perfect. So for these really weird systems that are in 4-day orbits, there's about a 10% chance of detecting a planet. So that means for every 10 stars that have one of these 4-day planets, transits can detect statistically one of them. For things that are more Earth-like orbits, 1-year orbits, there's about 1 chance in 200 of a transit occurring, and therefore you're detecting about 1 system out of every 200. And for the planets in Jupiter-like orbits, 12-year orbits, there's about 1 chance in 1,000 that a planet will be so perfectly aligned you can detect it. So as you move further out, you have a much smaller detection probability. So transit programs must survey many thousands of stars. As a result, transit surveys are typically forced to observe much more distant stars. So the first few transit planets were found from the ground. But the next great advance in transits was the Kepler mission. Kepler launched around 2009. It began finding planets around 2010. And it continued its primary mission until 2014 when it had technical difficulties. Kepler is about a 1-meter telescope that was launched in orbit, and it stared at one single patch of sky for the entire mission for 4 or 5 years. So all the stars in this beam is what it could see. It saw nothing else. That's all it did was stare at it. Took a measurement of the brightness of all the stars in this field every minute or two and sent it back down to Earth to look for these little dips. So in comparison, Doppler velocity, see this ring here? That's 3,000 light years. Doppler velocity seldom observes stars more than 150 light years. So this little space right in here is all Doppler velocities do. So you can see these things they're complementary, but they're very different. And one of the problems with really distant stars is it's not really possible to follow up with other techniques. Stars are very far away, they're very faint, it's very hard to get a Doppler velocity measurement. I mean, the holy grail in this business remains direct detection. You will never directly detect planets that are thousands of light years away. It's simply too hard. Direct detection requires the very nearest stars. So in one sense, things like the Kepler mission are primarily statistical. So here's a little overview of basically where we are now. I got this from the Exoplanet Archive at IPAC in Caltech like 2 weeks ago. And this is a histogram in year versus the number of detections, and they're color-coded so that the red is the radial velocity, and the green are the transits, And as you can see, they dominate. There are a few other types of ways to detect planets, but they've contributed very little to the field so far. And the very first planet is, there's one. Actually, I think it says 95, that's when it was announced, but I think it was first published in 96, and there's a teeny, you can barely see it, one little thing there. But you can see slowly, year by year, the Doppler velocity detections went up and continued to dominate until sometime after Kepler. So Kepler began returning planets in 2010, and very quickly the number of planets that was found from transits totally dominated the number found from radial velocities. So the advantage of radial velocity detections is that you're focusing on the nearest 4,000 stars, systems that can be followed up in detail with future programs, and with sufficient measurement precision, you can find almost all of the planets hidden in the overwhelming glow of the stars. The advantage of transit detections is that you can survey hundreds of thousands of stars and zero in on the smallest planets at the cost of limited follow-up. So here's another overview of kind of where we are in the field right now. And again, the things are primarily color-coded. Red is radial velocity, green is transits. This is the orbital period of the planet in days. This is a logarithmic scale. So there's 1-day planets, 10-day planets, 100-day planets, 1,000, 10,000, 100,000, and so on. And this is the mass of the planets, again, logarithmically scaled. 1 Jupiter mass, 1/10 of a Jupiter mass, which is about 2 Neptune masses, 1/100th of a Jupiter mass, and then the other way, 10 and 100 Jupiter masses. And you can see that there are distinctive clumps of planets. There's a lot of things that are relatively low mass. This mass range right here is in the realm of sort of Earth mass to Neptune mass, Neptune being about 15 Earth masses. And you can see there's a fair number of Doppler velocity detections, but an even larger number of transit detections. And this is the home of what we now call super-Earths. Again, another class of planets that were never, ever predicted. And most of these are now in transit detections, but the original ones were all from Doppler velocities. Then there's these much more massive planets. These are now Jupiter masses. These are the hot Jupiters. Again, there's a fair number of Doppler of radial velocity detections, but again, it's dominated by transits because they've simply surveyed so many more stars. But transits have a problem as the orbital period gets longer. As the orbital period gets longer, the chance of a transit dramatically falls. And furthermore, you need to observe 2 or 3 transits. So you see here somewhere around 100 days or so, transits sort of peter out. And almost everything we know about longer period planets, we've learned from Doppler velocities. There's a huge bonanza for the planets that can be detected by both transits and radial velocities. Both the planet radius from transits and the planet mass from radial velocities can be determined. From this, the planet's density can be immediately calculated. We can now move beyond just detecting the planets and begin to characterize the planets. This has been the goal of the second great NASA transit mission, TESS. So TESS launched a few years ago, and it's basically got 4 smallish telescopes, 4 small cameras that see huge hunks of the sky, about 24 degrees on the side, and they're just lined up in a straight line. And they're arranged so that the top view is through the ecliptic pole of the sky, and then they simply go down, down, down towards the ecliptic. And it sits in this path, in this pattern, for about 27 days. And then it shifts over to the next stripe, and then it shifts over to the next stripe, and so on, as as TESS and the Earth orbit the Sun. And the ecliptic plane gets observed the entire time. As you shift and shift and shift, you're always observing the ecliptic plane. So this tells you how many consecutive days you get in each one of these stripes. So at the ecliptic pole, you get basically 351 consecutive days of observing. So you need to observe at least 2 transits to make a detection, preferably 3. So with this means you can now find planets that have orbital periods up to about a half a year. Then as you go down, this band here, this yellow band, you get 189 days consecutive. So that gives you about, you can find planets out to orbital periods of about 90 days. And the blue is 81. These stripes here, I'm not even sure what color this is 54 days of continuous observing. And then most of this area, this light blue, this is the 27 days, because every 27 days the cameras shift to the next patch of the sky. So you can now find planets with orbital periods maybe a little bit less than 2 weeks. The huge advantage of this, of using smaller telescopes, smaller cameras, is that you're specifically targeting brighter stars, and you can also see a bigger patch of the sky. So the TESS mission can find stars brighter than about 12th magnitude within about 1,000 light years, so that they are much closer on average than the Kepler planets. And they're in a realm where, with big telescopes on the ground, we can follow up with Doppler velocities. And because TESS is moving around the entire sky, unlike Kepler, it sees 85% of the sky, a patch that's 400 times larger than what Kepler saw. So the whole mission is designed specifically to do bright stars so that they can be followed up with Doppler velocities. And we've been doing that here at the Carnegie observatories with the Magellan telescope. Steve Schuckman is somewhere in this audience, maybe Jeff Crane. They designed and built this thing specifically to get this amazing precision. And another one of our colleagues, Johanna Teskey, has been one of the major players in the TESS mission and following up with Magellan to get velocities and masses. So here's a chart that shows a bunch of these TESS discoveries where we're plotting planet mass and a mass of Earth now, 1 Earth mass, 2 Earth mass, 10 Earth mass, and so on, and planet radius, again, in Earth radii, so 1 Earth radii, 2 Earth radii, and so on. And you can see, to first order, this thing kind of looks like a scatter diagram. But because we now have the radius and the mass, we know the density. We can now start guessing what the composition is. And we can ask ourselves, theoretically, if the planet were made entirely of iron, what line would it fall on? And then Earth-like composition, which is an iron core but mostly rocky mantle. And then a pure rocky planet, that's this dotted blue line. And on up to the top one if the planet were composed entirely of water. And now you can see these planets fall in families, in classes. There are a couple of these very oddballs that are probably mostly iron. There's a bunch of planets that have a composition that appears to be similar to Earth. There are planets that are a little bit less dense and they have less iron in the core, but not too dissimilar from the Earth. And then there are some of these real wacky jobs that are extremely light, very, very little density, some of them even less so than water. So this is a great step forward. I mean, making discoveries is great, but this is science. You want follow-up. So I'm going to talk a little bit now about the future of this business. This is one of these NASA roadmaps, so it's entirely focused on space missions. And of course, you know, Kepler is gone. Hubble is pretty old at this point. TESS we've just talked about. Another mission that has just launched in the last few months is the James Webb Telescope, a 6-meter telescope, which will soon begin returning science data. And the exciting thing is it might be able to begin addressing the chemistry of the atmospheres of these planets. So, you know, we found planets, that's great, and now we can begin to characterize them in terms of what their composition is. And the next step is to begin to understand their atmospheres. Because, you know, in the end, we want to know, these things have life? I mean, that's the big driving question. And then another mission that's going to launch, hopefully in the next few years, is WFIRST. And the most exciting thing it will be able to do, potentially, is direct imaging. Direct imaging, so the stuff in blue, everything from here over, this is all launched, this is all done. This hasn't launched yet, but it's in blue because there's real money. This thing is going to launch. I mean, I don't know if it's going to launch on time, but it's going to launch. The stuff in gray is more speculative. And the stuff over here, 2035 and beyond, come on, folks, I'm 62. I don't care what happens in 2035. So I'm going to basically talk about Webb and W first and the star shade, which star shade is an add-on to W first. So the first thing, though, is Webb and atmospheric chemistry. So we would love to be able to get spectra of planets, of their atmospheres. If you saw oxygen and water vapor in the spectrum of a planet, that would be spectacular. I mean, it wouldn't prove that these things had life, but it would really flip the question. It would no longer be a matter of like providing hardcore proof it has life. You would almost have to prove why it doesn't have life. Oxygen is a wild molecule. It is incredibly reactive. If there was no life on Earth, the atmosphere is 20% oxygen. If there was no life on Earth, that oxygen would all go away in less than 400 years. It would just react wildly. It would react with rocks. It would get bound up. And the only reason we have oxygen is because the Earth is wildly out of thermodynamic equilibrium. And the thing that makes it out of thermodynamic equilibrium is life. So it turns out there is a trick now that you can use to make a direct measurement of the atmosphere of a planet, even though you can't really ever see the planet. And this goes back to our good friend transits. So as a planet transits its star, to first order, the planet simply acts like a black dot. But to second order, around the annulus of the planet, light from the star is going through the atmosphere, and it's continuing on to the observer with the telescope. So if you can take really good spectra of the star by itself, and then really good spectra during the transit, and take the difference will be the spectrum of the planet. And this has actually been done. This was done with the Hubble Space Telescope for the very first transiting planet that was discovered back in 99. I think this was probably done in the early 2000s. And so here's the gray line here is the spectrum of the star. And this extra bit here in blue, that's the additional spectrum that's specifically due to the fact that some of the light passed through the star's atmosphere on the way to the Hubble Space Telescope. And JWST will be dramatically better than anything Hubble can do. Hubble is a 2.4 meter telescope. JWST is 6 meters. And it's specially optimized to work in the infrared, which is where most of the interesting molecular features are in. So I think this is going to be gangbusters over the next 5 or 10 years. Now, the other mission I mentioned is W first, and this will hopefully launch in the next 5 years or so. It will launch, but I don't know how much faith you place in anybody estimating those space launches within a year or two. So this will do great things, but there's this other proposed follow-up mission which will go up into the 2030s, and it's called Starshade. And it's this giant, it's what it is what it is. It's a star shade. It's this giant thing that launches, that is totally separate and independent from the telescope. It would be separated from the telescope by about 20 to 40,000 kilometers. So it's a long way away. You can't drive there. And what you would try to do is line this star shade up with the telescope such that the star shade perfectly blocks a background star. Right now, it's impossible to see the planets because they're lost in the glow of the star. Even a giant planet like Jupiter is about 1 billion times fainter than the sun, and it primarily shines just by reflected light. So, and if you're looking at it from many light years away, you've got this one incredibly bright star, and then you got this teeny tiny little firefly that's 1 billion times fainter that's right next to it. You can't pull the signal out. But with a star shade, you can knock down the signal from the central star, and there's the prayer that you would be able to directly see the planets. And then we would finally maybe be getting to where the holy grail of this field is right now, directly imaging extrasolar planets and being able to directly take spectra of them. I mean, that would be a huge change, and it would put us in the position where we might be able to begin seriously addressing the issues of life. So while transit surveys and direct detections are best done from space, radial velocities are best done from the ground, and they're uniquely able to measure the planet mass. Radial velocity surveys done from the ground are dirt cheap compared to space-based missions. The James Webb Space Telescope, which just launched, is a 6-meter telescope, which cost $10 billion and was launched almost 20 years late. For comparison, a ground-based 6.5-meter telescope with the world-class radial velocity spectrometer costs about $100 million, a factor of 100 less. So when I say pennies on the dollar, I should amend that. It's 1 penny on the dollar to build ground-based systems like this. And they can be easily repaired and upgraded with the latest technology, unlike anything in space. So one of the recent examples of how this old-fashioned radial velocity from the ground continues to pioneer the field is the recent discovery of Proxima Centauri. So Proxima Centauri is the nearest star in the sky. It's about 4 light years away. It's the guy who lives right next door to us, right? The next door neighbor. And here we see, this is from around 2016. This is a combination of data from a couple of telescopes. UVES is an 8-meter telescope that's run by the European Southern Observatory. HARPS is another telescope run by the European Southern Observatory. And you see there's 3 sets of data. UVES are the triangles. The squares are the older HARPS data. And the brightly circled dots are data that were taken every single night for about 3 months. And we were able to pull out this signal that's got an 11.2-day period and an amplitude of about 1 meter per second. So this is really state-of-the-art. The resulting planet is about 1.3 Earth masses. The period's 11.2 days, but it's orbiting this teeny tiny faint little red dwarf star. And it turns out for these faint little red dwarf stars, which are only putting out about 1% as much light and heat as the sun, that's the habitable zone. That's the space where, if it would be the right temperature, that it could potentially have liquid water on the surface. So this also got a huge amount of publicity at the time, and I love the Nature cover for it, Near Horizon, because this is as close as it's ever going to come, folks. And it also points out that we've answered a couple of the other questions in this field. One of the initial questions was, what fraction of stars have planets? The very nearest star has a planet. Almost every star has planets. I'm not going to say it's 100%, but it's probably 99+% of stars have planets. So this brings us towards the conclusion of this talk, which the title promises Alien Worlds and the Origin of Science. So I haven't directly addressed what I consider the origin of science. In my opinion, science was invented by Kepler in 1607. After struggling to fit the orbit of Mars with the Copernican model for several years, he made one slight tweak. He maintained circular orbits for Earth and Mars, the perfection of the heavens, but he shifted the sun slightly from the center of these circles. He produced the most accurate and easiest to calculate model ever, but it did not quite match Tycho's measurement uncertainty, so he threw the model in the trash. That's when science was invented. The model must fit the data within measurement uncertainty. So Kepler then spent the next 12 years coming up with the 3 laws of planetary motion, which I won't go into because otherwise I'd have to give you a quiz afterwards. These 3 laws of planetary motions are the same 3 laws that we use to calculate the orbits of extrasolar planets today. They're the same 3 laws that Newton used as a stepping stone to universal gravity. They're the same 3 laws that Einstein used as a stepping stone to general relativity. The amazing thing is that during this period of development, Kepler was slowed for several years because his mother was being tried as a witch. He literally had to take time off from being an astrophysicist and be a lawyer to defend her from a charge of witchcraft. So here we are 400 years into the scientific revolution, and as far as I can tell, we're still in the world of witchcraft. Okay, well, thank you very much.
If anybody has any questions, please head to one of the microphones, either where I'm standing or across the room over there.
Why does the sunshade have the shape that it has?
That's a question which is way too technical for me to answer. It turns out if you have a perfect circular shape, you get all sorts of weird diffraction patterns, various rings and so on. So people have run gazillions of optical simulations to try to figure out what shape would minimize that and give you a better chance of being able to find the little hidden planet.
Did you speak about, like, Mount Palomar use their adaptive optics system to actually image exoplanets? And of course you can't see anything, but what you can see is you can see the transit for real. And I understand other observatories, earthbound observatories, have had similar success using adaptive optics. Can you speak to that?
Yeah, adaptive optics is a wonderful technology. So the problem with observing from the Earth is the starlight has to come through the atmosphere. And the atmosphere is bubbling and boiling and moving all around, and each little piece of it is its own little lens. It's distorting the light this way and smearing it out. And adaptive optics is a technique where you have what's called a rubber mirror. You have somewhere in the system, maybe more than one place in the system, you have a mirror which can be tweaked about hundreds of times a second so that it tries to remove all of this jiggling from the atmosphere. And there's been great successes with this. You get dramatically clearer pictures with these adaptive optic systems. And so Palomar has it, the Keck Observatory has it. They're working on these systems for all the new giant telescopes. They will still never be as good as going into space.
However, they're very cheap to make modifications to extend the technology. So I know the European Space Union, they're building also the giant Magellan. All these technologies are using something like adaptive optics, and is there an expectation that they will be able to validate these exoplanets that are being discovered by these satellites, or are they just pointless?
Oh, they're not pointless. They're already producing great science, right? I mean, like, even if they're not finding exoplanets. And I think, honestly, your question is really good, because there is kind of a race right now between these, multiple billion-dollar space things to find exoplanets directly, and the next generation of giant telescopes. These things are going to be 25, 30, 40 meters across, and who knows what you're going to be able to get with advanced optics and advanced computing. It's going to be a horse race to figure out which one actually manages to find planets first.
So an interesting theoretical question is, I notice as an amateur astronomer, there are telescopes now, you basically put it outside and let it point to the sky and it finds things. Pretty amazing, and it surprises me that these telescopes don't yet use the movement of the Earth to do multiple measurements to improve the accuracy of the measurements. Kind of like the interferometer they have at Mount Wilson. They've got 2 points far apart, which allow huge accuracy into identifying or measuring something. It surprises me we don't yet have that kind of connectivity with our telescopes such that we can do that with multiple ground-based telescopes.
So we do, but it works in the radio. It's much easier for these things to work for radio interferometers to work than for optical interferometers. Radio interferometers, the wavelengths are long, and you can put them together from remote distances. For optical telescopes, the wavelengths are teeny tiny, very small, and things get dramatically harder. But, you know, it's another technology that, you know, the next generation or two may emerge.
So are these being actively used to identify exoplanets and quantize them?
I don't think the ground-based optical interferometers can get in that league yet, but there is this huge brand new radio telescope array in Chile, which from the radio, it appears, should probably be able to detect exoplanets.
Okay, well, I'll ask these same questions in a future talk because we have the Giant Magellan Telescope being discussed.
Thank you.
One of the slides said that the planet was tidally locked, and I was just curious how we know that.
Yeah, so for these planets that are in very short orbits, like in these 4-day orbits, the star is going to raise enormous tides on the planet. And theory suggests that the planet should be locked to it such that one side always faces the star. And a really common, obvious example of this is the Earth and the Moon. We're so close together that the Earth raises these huge tides on the Moon, and the Moon has got one side, one face locked to the Earth. Whether this actually, so we can't actually measure this right now for extrasolar planets. We can't measure the rotation rate of the planet, and it would be lovely to know. When theorists tell you something, I don't know, you should take it with a grain of salt, right? Wait until you can make a damn measurement. You know, if it was up to the theorists, they would almost certainly tell you that Mercury is tidally locked to the sun. There is a tidal locking, but it's not one-to-one. Mercury does not keep one face to the sun. So it's an interesting line of inquiry, but it's sort of beyond the ability to make measurements right now.
Hello. Can I ask a kind of silly question, but what's the point of finding all this information? As in, do you think that we will all have to leave the Earth at some point?
So part of being really old is I don't hear very well.
Oh, I'm sorry. I said, kind of, what is the point of of finding all this information in a way of like, do you think we have to leave the Earth at some point and move there?
Yeah. So in my experience, good planets are hard to find. Astronomy used to have a real role in civilization. One of the jobs was we kept time, we kept calendars, we helped farmers plant things, you know, for the seasons. We had a job. That's all gone. I mean, the last thing we did that was of any value is we did keep time into the 1950s, but the physicists stole it from us. We can't match the atomic clocks. So the field is largely curiosity-driven. Right now, it's just we want to know, right? But you know, that we don't see any. You know, it's not like we know of any way to get there, right? But that's not to say it's impossible. So Kepler, on top of all of his other amazing accomplishments, wrote the first science fiction novel of all time. He wrote, like in his day, the amazing thing that you could contemplate was going to the moon. So he's pre-Newton. He doesn't have rockets. You know, he doesn't have F equals ma. He doesn't have any of this stuff. So his propulsion mechanism was you take a ship out in the ocean, and it gets caught by a hurricane, and it gets flung to the moon. Okay, but you know, 400 years later, people went to the moon, right? I mean, so the stuff we're doing today, it's not going to have any immediate return for people. It's simply curiosity. We want to know where we are. We want to know our relationship to the universe. We want to know, is there anybody else out there? I mean, right, that's the driving thing. And what happens in 300 or 400 years, you know, I'll be long gone, right? But if it's of benefit to people at that time, you know, power to them.
Oh, hi. Yeah, you know, there's been some discussion about kind of along the same vein as the question before mine, which is we're looking at these telescopes and looking at the imaging, and I'm just wondering, is there a plan for how to get these telescopes, how to get these different machines down from space in a safe way, or even just how do we get these down from space? Are they just floating out there forever, and we'll be gone, but what about the generations after us? And what are the impacts of those?
Spacecraft that are orbiting
Spacecrafts, all of these imaging systems that you've been mentioning,
Yeah.
those that are out in space or outer space, how are we going to get those down?
They send the data down now using radio waves, right? But they're not coming down because it costs too much to bring them down. They're just up there. They're not coming down. If they're in low Earth orbit, they may eventually degrade in orbit to the point where they hit the atmosphere and they'll burn up. But for things like TESS is in a really weird orbit. TESS is in an orbit that's out of the plane of the Earth-Moon, and at its furthest point, it goes out as far as the Moon. At its nearest point, it comes relatively close to the Earth, and it does 2 orbits of the Earth every time the Moon does 1 orbit of the Earth. Very strange orbit. That's going to be good forever. That's just going to be floating around for a gazillion years. TESS itself may last another 10 years, which would be great, but after that, it's just going to be this dead thing that's orbiting the Earth.
So are there any discussions about all of this space waste that we're creating out there?
So the space waste issue is a very serious issue, but for things like TESS, it's not. Things that are in distant orbits, they're fine. It's all the crap that's in the near-Earth orbit. That's the problem, where the space shuttle and everything, and all the satellites and everything that are in these inner orbits, those are the ones where they're in danger of getting hit by other space junk. Things in distant orbits, you know, when it gets to the point when those orbits are all filled up, man, that's going to be a wild time.
So I think one of the points is that as we talk about the supremacy of science, implicit in that is that we're not discussing the waste and the implications for the future and sustainability, as well as as we're discussing space waste, we can just dismiss this. But even here on our planet, as we look at the degradation of this planet and looking at supremacy of science, what is contributed to
the vast number of the satellites that are in near-Earth orbit aren't science, right? They're communications, they're this, they're that. I mean, the number of actual astronomy satellites is very teeny. I mean, this is not the problem. And typically now, the astronomy satellites are going in these much more distant orbits to get away from the Earth, not because of space waste, but just because the Earth is so bright. So astronomy satellites are not an issue. There is a big issue, right? But astronomy is not really a serious contributor to this.
Thank you.
Yeah.
Hi, I actually had a quick question. On the slide that showed the graph with the mass and then the orbit of the planets, most of the planets were clustered together, but then there was one planet that was far off to the right, which seemed to have an orbit of 10 to the 5th power. What is that planet?
Let's see if I can find the slide. Not that one?
Not that one.
Okay. That one. Yeah, okay. So this thing that's way out here, you'll notice that's imaging. And I've already said that imaging is impossible. It is possible to image planets. Very, very few. You'll notice there's only a handful of these directly imaged planets, these blue stars. If a planet is orbiting a relatively nearby star, and the star is super duper young, and the orbital distance between the planet and the star is huge, it is possible. So the further the planet is from the star, the less the planet is going to be hidden in the glare of the star. So that helps. Then if the star is very, very young, that means the planet is still coalescing out of the cloud of gas and dust. And as it's coalescing, that's heating up the planet. So especially if you go into the infrared, the planet then becomes much brighter. And if it's very far from its star and it's around a very nearby star, a handful of these things have actually been observed. So that's one of these cases. And you'll notice in all of the cases of direct imaging so far, They're all in very large orbital distances. There is no technology now that would allow us to find one of these things in a small orbit.
Thank you very much.
Yeah.
Hello. Sorry, I have a question. Is that your
How about just one last question, and then we'll call it quits. Go ahead.
Hello, I have a question. So why for the planets that's found by microlensing, why are they only between 10 to the third and 10 to the fourth period days?
Again, I'm having trouble hearing.
Sorry, so for the planets that's been found by microlensing, why are they only in between 10 to the third and 10 to the fourth days?
So the planets in the Kepler mission, you're asking why they have to be distant?
No, for microlensing, they only exist, from what I see in the graph, they only exist from 10 to the third to 10 to the fourth days for their period. On that graph. They're like a straight line.
I need to pick one person here to tell me what's being said. You tell me what's being said.
Purple triangles, why are they all in that one vertical plane?
Okay. So again, I glossed over microlensing for the same reason that I glossed over the imaging. There's just so few of these things. So microlensing planets are an especially odd class of planets. They come from Einstein's prediction from general relativity that when light goes by a star, the star's mass will actually bend the light. And then it turns out, the way these measurements work is you look at some background field, like the Large Magellanic Cloud or the Andromeda Galaxy or the core of our own galaxy. Some background field that just has gazillions and gazillions of stars densely packed. So that's your background. So then if you have a foreground star, a star in our own galaxy, or it could even be a star in another galaxy, and it goes in front of this, and it lines up perfectly, or almost perfectly, with the background star, then the light going past the foreground star will amplify the amount of light. And so if you're tracking how bright the object, you're looking at some star and you're tracking how bright it is, and the star's brightness is the same, and then suddenly it'll climb up because you've got this Einstein effect, where the two stars are perfectly aligned, and the foreground star is amplifying the background star gravitationally. So then if on top of that, this foreground star has a planet, instead of just getting a smooth amplification curve, for a day or two you can get this wild spike. It's a very strange situation where you never see the planet. Of course, we never see the planet either. Often you never even see the star. You don't even see the foreground star. All you see is the Einsteinian amplification of the light of the background star by the foreground star, so you infer its existence. And then furthermore, you're just looking for this weird spike, which only lasts for a day or so if it has a planet that's just perfectly aligned on it. And why these things are all in orbital periods of order 10,000 years, or 10,000 days or so, I don't really know. But the truth is that the error on these periods is huge, because they actually don't know what the periods are. They get one observation, the detection lasts less than a day, it can never be followed up by any technique ever again, and so there's very little you can do with this stuff. Our friends at IPAC felt obligated to include it, I guess, because of a sense of completeness.
Thank you.
Yes.